Muy buenas tardes a todos. Damos inicio en el día de hoy, noviembre 23, a la sesión del profesor Peter Molnar. Él nos va hoy a hablar de paleoaltimetría. Entonces, vamos a deleitarnos precisamente con esta conferencia. Thank you, Peter.
Thank you, Hector. So today I'm talking about paleoaltimetry. And just to start, I contend that 90% of the time the word uplift has been used to describe the development of a mountain range. The word was misused. The authors have placed no constraint on changes in elevation, which is the important part. And in many cases, the Earth's surface has actually gone down, not up. And yet, constraining paleoelevations is one of geology's greatest challenges. So this is a topic at the frontier, and most of the good work that's been done has been done only in the last 20 years. And before 30 years ago, essentially nothing. So just to back up and remind you, what can uplift mean? And this is a reminder. You can think of uplift of rock relative to sea level. This is what geodesy measures. A benchmark sits on a piece of rock, and one measures the uplift of that benchmark relative to sea level. Or with coastal terraces, one measures uplift relative to sea level. But there's also the uplift of the Earth's surface with respect to sea level. And this we can look at this as the mean elevation over a large region. If that goes up, the surface has gone up. The uplift of rock includes the uplift of the Earth's surface, but it also includes uplift of rock relative to the Earth's surface, with respect to the Earth's surface. So a metamorphic petrologist will find a rock that clearly had been deep in the Earth. It's now at the Earth's surface, and he or she might use the word uplift, but here the reference frame is the Earth's surface, not sea level, and the rock is moved with respect to the Earth's surface. And that measurement that the metamorphic petrologist has made is really better described as exhumation. The rock at depth has been exhumed by the removal of rock above it. So using the word exhumation, we can turn this around and say surface uplift is uplift of rock relative to sea level minus exhumation, which is rock relative to the Earth's surface. And so geodesists measure this, metamorphic petrologists measure that, but what we really care about is this. This is where the energy goes when building mountain ranges, the uplift of the Earth's surface. And this is the challenge. This can be easy to measure. This can be easy to measure. The difference is not necessarily. So there are two families of approach in this. One can depend on air pressure decreasing upward, as it does in a simple way, exponentially, with an e-folding height of 8 kilometers. So when the height is 8 kilometers, the pressure is reduced by 2.7 times. And concentrations of major gases also decrease exponentially. Water vapor, it's complicated. H is 2 to 4 kilometers. For CO2, again, it's about 8 kilometers. Also, air temperature and related quantities, and moist enthalpy is one that I will introduce, it's important, decrease with elevation, but less simply than pressure. And so we rely heavily on temperature, but one of our challenges is to determine how temperature decreases with elevation. And I would argue geomorphology cannot, in general, constrain paleoaltimetry. Geomorphology is fun, it's important, it's useful, but this is not where its use lies. So I'm going to describe 7 possible approaches to paleoaltimetry. First, paleobotanical constraints on paleoenvironments and hence on elevations. And this really relies on temperature, though I will use moist enthalpy. Oxygen isotopes and deuterium, hydrogen isotopes or deuterium, precipitated in rainwater and concentrated in sediment, they decrease with, or they change with elevation. And again, that depends on temperature. Clumped isotope measurements of temperature. If you don't know what this means, I will describe it, but it's a direct measurement of temperature. And BRGDTs, again, I will tell you what these are. If you don't know, these are organic molecules. They also can be used to infer temperature directly. Then on the pressure side, there are pressure sizes of vesicles in lavas. Vesicles are bubbles that have been frozen when the lava cools. They're erupted at the Earth's surface, and they depend on the pressure. The higher pressure, the smaller the vesicles. The concentration of cosmogenic nuclides produced in surface rocks by cosmic rays also depend on pressure, as I will show you. And finally, the stomatal density of leaves depends on the pressure, the PCO2, pressure of CO2, which decreases elevation. So this is a pressure measurement. And I'll describe all of these in more or less detail. Starting with paleobotany, there are actually two approaches. I'm going to focus on only one of them. One of those, and not the first, one of them uses nearest living relatives. So one finds a fossil piece of an organism, like a piece of pollen or a leaf or a piece of bark, assigns taxonomy, hence a Latin name, according to similarity with nearest living relatives. This is the way this is done. Then one finds a present day environments that contain assemblages of nearest living relatives. So one has all of these nearest living relatives. One tries to find a similar region, and then one equates the paleo environment that contains the present day present day taxa with the nearest living relatives found in the fossils. So one equates the paleo environment of the present day environment that contains these nearest living relatives to that of the past. Leaf physiognomy takes a different approach. One characterizes present day leaf shapes and sizes, and I'll describe this further. It relates their statistical distribution to their present day environments. Again, this is getting at temperature, humidity, or some other quantity. And then one measures the shapes and sizes of fossil leaves and relates their statistics to that of the present day environments to get at the paleo environment. The key assumptions are different in these two. For nearest living relatives, one first starts with taxonomy, and that's difficult to assign reliably to fossil plants for a couple of reasons. One is one rarely finds a complete fossil plant. One finds a piece of pollen, a leaf, a piece of bark, a piece of wood, a piece of root or something, and one doesn't see the whole plant. So this makes it difficult. One could actually give the same plant with the different pieces of that plant 5 different Latin names for the 5 different parts. And then it assumes the similarities to modern plants can be applied to past environments. So that ignores evolution, and it risks on focusing on plant organisms that are insensitive to climate, the ones that preserved well. It also assumes that the taxonomic assignment can be done reliably, and the fossil record, as I said, rarely contains entire plants. So this can be done well. It has been done well. I'm not going to discuss it. But let me say that recently in Colombia, at AFIT, a very good young paleobotanist, Camilo Martinez, was recently hired. And if this is something that interests you, I urge you to contact her. She knows this well, much better than I do. And she's done good work using this approach. It can be done, but I'm going to focus on leaf physiognomy. Here, the basic assumption is that the physical and chemical, and therefore environmental processes, affect leaf margins and leaf sizes. So these leaf margins and sizes are a consequence of the environment. They depend on that environment. And the processes responsible for them have not changed over geologic time. In simple terms, to exaggerate this is assuming that the laws of physics today apply to the laws of physics back in the past. That exaggerates this view. So there are 2 steps with leaf physiognomy. First, relating leaf shapes and sizes to properties in modern environments so that we have a background, something we can use for future studies. And to put this in context, here are photographs of different leaves, and you can see they're different. You have no trouble distinguishing all of these. They can be long and thin, as this one or this one is. They can be fatter. They can even be wider than they are long. They can have teeth. Teeth are very important. These have teeth. Teeth are hard to see. They're small. Here the teeth are easier to see. These have no teeth and no teeth. The leaves clearly are different in different environments. One uses the term non-entire margin for leaves with teeth. For leaves with no teeth, entire margins is the term. And to just give you some examples, take this leaf on the left. It's lobed. There are 3 parts to it. It has an acute apex. Up here it's sharp. A round base. It's round down at the bottom. And it has no teeth. This leaf, B, has an ovate, an egg-shaped, it's an egg-shaped leaf. It has a round base. Down here, it's not, sorry, this is an egg-shaped leaf. It has an attenuated apex, sharp apex up here, and it has a chordate heart-shaped base. As a base down in here is the opposite from this, or an opposite direction. And C, again, is egg-shaped, but upside down. It has a round and a marginate apex. This apex is opposite, and it has an acute base. It's sharp down in here. And again, no teeth. Teeth are illustrated in this example. Teeth are the best of all of these. If one plots the percent entire margins, that is no teeth, percent on this axis, percentage of species in a forest, so one goes into a forest with 30, 40, maybe 100 different species of trees and shrubs that have leaves, one takes the percentage with no teeth and plots that against mean annual temperature. Well, in the tropics where it's warm, teeth are rare. In the colder environments down here, entire margin species are rare, and therefore teeth are common. Teeth are the opposite of entire margins. And I should say this general trend was observed more than 100 years ago. This has been known for a long time, though Kate Gregory, she added a bunch more data with help from others to make this plot. If one looks at other features, for example, the length to width ratio, these are short, fat leaves. And here are 7 different environments. California, this is a moist but high environment. Pennsylvania, temperate. Hokkaido, Japan, temperate. And now we move into colder or to warmer regions in Sonora and into Florida and Puerto Rico. Here, the length to width ratio, these are wide leaves. These are much more common in temperate environments, cooler environments than in the warmer ones down here. Again, no teeth. No teeth are rare. Teeth are common in the cooler environments, and no teeth are common in the warmer environments. And then one can dig in and look at other qualities. Lobed leaves. Lobed leaves tend to be more common in cooler environments. Small size varies in that way, but also depends upon aridity. Dry environments like Alamos, Sonora have many small leaves, whereas small leaves are not so common in wetter temperate environments. Sierraville, California is a drier environment. So these various parameters vary from place to place, and one can do statistics on them. So what one does is one relates the leaves and sizes to properties of modern environments, and then applies that to an assemblage of fossil leaves to determine a paleoaltitude. And this determining the paleoaltitude, I remind you, this requires taking into account changes in climate, because today climate's not the same as the past, and therefore requires inferring what the climate would have been at sea level in the past nearby. That's another step in using this. So to use leaf margin size, we must measure a quantity that depends on elevation, and one can use temperature, but for reasons that I will discuss more, it's not that good an elevation parameter. It's necessary for some tools, but it's not the best. Pressure, leaves don't care about temperature. And what we turn to is moist enthalpy, which I will describe, because moist static energy, this is the key quantity, is a thermodynamically conserved variable in the atmosphere. So moist static energy, let's start with this. Moist static energy, written with a little h, consists of an internal energy, the heat capacity at constant pressure times the temperature, plus the latent heat the latent heat of vaporization times the fraction of moisture in the air. If the air is completely dry, this is 0. This can get up to be a few percent at most, plus the potential energy. Kinetic energy is negligible. One can throw it out. It's very small. And I remind you, this is per unit mass. So this is potential energy per unit mass, hence G, gravitational acceleration, and Z times height. And these quantities all vary over the same range. So the first we have to test, is moist static energy a thermodynamically conserved quantity? And is it zonally invariant so that we can, that means no variation with longitude, so that we can apply it? So here's a plot of moist static energy, the mean annual moist static energy as a function of latitude in North America. It's high and low latitudes, 335 kilojoules per kilogram in the units, going up to only 270 or 260 at high latitude. So it decreases with latitude, and it's pretty much zonally invariant. There is variation, so there's scatter. And on a plot of latitude versus moist static energy, you see a definite trend, but with definitely a scatter as well. So we use this, and we use the uncertainty that comes from this in calculations, because we're going to rely on this conservation of moist static energy. So how do we do that? Well, from the plants, we're going to infer a quantity called moist enthalpy. Moist enthalpy is the internal energy, the part that depends on temperature, plus the latent heat, the part that depends on moisture. It does not include the gravitational part over here. So this is moist enthalpy, and I will show you in the next slide that we think we can measure, using leaf shapes, moist enthalpy. And the logic is simple. If moist static energy is conserved, so the air here has the same moist static energy here along a line of latitude, but here, because we're at sea level, Z is 0. At this point, down here at this level, the moist static energy equals the moist enthalpy, what you measure. Whereas at this elevation over here, one measures, again, moist enthalpy, but the moist static energy includes the potential energy, GZ, over in here. And we're saying that the two H's are equal to one another. And if they're equal, then simple algebra says the height is the difference in moist enthalpy divided by gravity. Very, very simple formula, easily applied. How well do we do? Well, what Wolf, not Forrest, in fact, Wolf is a co-author here. What Wolf did was went to many forests around the world, and where there were many different species of trees, forests, and for which there was a meteorological station. So he could go to the meteorological station and estimate what the mean annual moist enthalpy is, plotted on this axis, and then he could take the statistical relationship that he derived from the leaf shapes and sizes and predict a moist enthalpy, and he got a plot that looks like that. And you can see a very definite trend. He could do the same with temperature. Again, he goes to a forest where there's a meteorological station, measures the temperature, that's the observed, infers the temperature from the leaf shapes and sizes, and temperature is in fact clearly better than moist enthalpy. The logic here is moist enthalpy leads to a better estimate of elevation than temperature, but temperature we can do well. Specific humidity, the fraction of moisture in the air, again, not as good as temperature, but clearly a trend. One can observe that with a meteorological station, and one can predict it. And from these relationships, one can predict relative humidity. Not that well, but not bad. The uncertainties in paleoaltitudes that include the error in assuming zonal independence of moist static energy are given to be 800 meters. Call it 1,000 meters. Paleoaltimetry can make an estimate in these situations with an uncertainty of 1,000 meters, which is good, but we'd like to do better. So what does this require? It requires finding fossil leaves of at least 20 different taxa, and better 30 taxa or more, to get good statistics. It assumes that we can estimate moist enthalpy as well from these leaves. It assumes we know how moist static energy varies with latitude, and this applies to the past, of course. And for this reason, the method works better in the mid-latitudes where the air blows from west to east and thermodynamic quantities are conserved better. And it requires either that we have a site at sea level in the same latitude, or that we know past climates well enough to predict moist static energy at the surface. And then we just take that difference. And as an example of where this has been done in the Western United States, you'll recognize there's the Valley of California, San Francisco, Los Angeles, that we're talking of early Cenozoic time. And there are sites that were used on the coast. There's a site up here, and there are a couple of sites in California that gave us sea level estimates of moist enthalpy. But if you look in the north up in here, the red shows the paleo elevation, the blue shows the present day elevation. And in all of these places, the surface has gone down. The surface was higher back in these cases, Eocene time. In other places, it's about the same. Down in here, Green River Formation, Creed, these are about the same. Florissant may be a little higher. This may be an overestimate. The only place where we find that the paleo elevation was lower than the present day elevation is this Kissinger Lakes in here. And this is very near Yellowstone, where there's a hot spot. And this area certainly has gone up in the last 10 million years. And notice the age of this, I don't know if you can see it, but the age of Kissinger Lakes is 40 to 50 million years. So this is the only place that seems to have gone up, and it's the only place we really would be expected to have gone up. Okay, I'm going to switch to another method, oxygen isotopes as paleoaltimeters. The mass of hydrogen of water, H2O, when the oxygen is oxygen 16, is smaller than the mass when it's oxygen 18. And because of this mass effect, the binding energy among molecules is stronger for the more massive case. So this means that, well, we'll go on. This means that H2O, when it's 16, evaporates, enters the vapor more readily than the oxygen 18 water. The oxygen 18 water stays behind. And conversely, condensation of liquid water from vapor favors oxygen 18. Oxygen 18 goes into the liquid. Oxygen 18 would rather be in the liquid than the vapor compared to oxygen 16. And so it follows, as air rises over high terrain, it cools and vapor condenses, and then it precipitates, and hence the oxygen 18 rains out with that water vapor, and the vapor becomes increasingly depleted in oxygen 18. So precipitation over terrain at different elevations should contain different concentrations of oxygen 18 by this process. And as an example, this is delta O18 in precipitation. I think it's precipitation in Bolivia at different elevations. So elevations 1, 2, 3, 4, 5 kilometers elevation, and delta O18, the negative sign, this is increasingly depleted in this direction, and it follows a curve that's not a straight line, but it fits a curve, a quadratic curve, quite well. So this is an inescapable consequence for oxygen 18. But there are key assumptions. One of them is that the water evaporates once, only once, at low elevations, and it precipitates once and only once over higher elevations, different elevations, but higher. And obviously it precipitates, it condenses, and then precipitates where it falls. And then it accumulates in geologic materials. Buried in this is the assumption that the process responsible for precipitation, like thunderstorms or steady rain, haven't changed. Thunderstorms empty the air of oxygen 18 much more readily than steady rain. So a change in the style could have an effect. It assumes no re-evaporation on the onward transport of moisture. And this can be a problem because obviously if you go over a long distance, water rains out and then it re-evaporates and goes back into the atmosphere, and then it rains and re-evaporates. This makes it hard. This makes this approach useless. Moreover, there can be no change over geologic time in the source of the water. You can imagine water coming from high latitudes will be different. They'll have a different oxygen 18 fraction than water from the tropics. And so if the locus or the source of water changes, oxygen 18 will change, but elevations will not necessarily have changed. So these are restrictive assumptions, and it means this method works where mountain ranges are relatively narrow, not for places like Tibet, high, wide plateau like Tibet. And as an application, this is Carmi Garzoni's work, from the Bolivian Altiplano, going back in time, so 5, 6, 7, 8, 9, 10, 11, 12 million years. These are the inferred elevations from oxygen isotopes within carbonate sediment. And you see a rather abrupt increase in elevation sometime between 10 and 6 or 7 million years. We're talking about going from 1,500 to 4,000 meters, 1,500 plus or minus quite a bit, but still arguably a 2-kilometer change in elevation in a relatively short period of time. That's fast. So a shift in oxygen 18 in this period of time suggests the Altiplano rose 2,000 to 3,000 meters in only 3 or 4 million years, hence a very fast rate. This, and I believe this. I think this is reliable. So I'll come back a little bit to oxygen isotopes, but let's talk about clumped isotopes. And these give direct estimates of paleo temperatures. There's a theoretical basis for this and good experimental evidence. And it depends on this temperature-sensitive clumping of heavy carbon, carbon-13, and heavy oxygen, oxygen-18, in calcium carbonate. So in calcium carbonate, you'll have a calcium and then 3 oxygens. You'll have a carbon, you'll have a calcium someplace, but you'll have a carbon and 3 oxygen around it. And carbon can come in 12, with atomic numbers of 12 and 13. Oxygen comes as 16, 17, and 18. Most oxygen 16, most carbon 12. But you can have carbon 13 and carbon 18 in this, and these tend to clump together. These tend to join in the same carbonate ion more readily than if they were randomly distributed. And again, this is because they're heavy. So looking at it this way, you can imagine a carbon with a carbonate ion with carbon 12 and 1 oxygen 18, another carbonate ion with 1 carbon 13. They can make a clumping, carbon 13 plus carbon 18 in this one, and then an ordinary carbon 12, carbon 16 over in this case. This is now treating this as carbonate, sorry. And what one does is one reduces this to a CO2 molecule, so one gets rid of one of the oxygens, because then it's easy to measure. You can put carbon dioxide in a mass spectrometer and measure easily. So you can imagine the common version of a carbonate ion is a carbon 12 and a oxygen 16 in all places. But you can have carbon 13 instead of carbon 12, or you can have carbon 18 in one of the oxygen slots. But when you clump, these two are together. That's this case. And the point is that this is favored because of the higher masses of these molecules. They clump together. Theoretically, this should occur more often than you might expect. And if you reduce this to carbon dioxide molecules, then the normal, a 12 plus 2 oxygen 16s, gives you an atomic mass of 44. But if you combine a carbon 13 and an oxygen 18, you get an atomic mass of 47. So this is called the delta 47 paleothermometer, because what one does is one measures the ratio of carbon dioxide molecules with a atomic mass of 47, most of which are oxygen 18, carbon 13, but they can come in even likely combinations. The ratio of that to the normal, ordinary carbon 12, oxygen 16. And one then takes what's measured and then randomly distributes all the carbon 13, 18, 17, carbon 13, oxygen 18, oxygen 17, randomly distributes them in a stochastic version, takes that ratio, subtracts 1, because this is going to be larger than this, multiplies by 1,000 to express it in parts per mil. This is what is called delta 47. And this works, as I said, because these two clump together when it's warm. Oh, sorry, when it's cold. This depends on temperature. Theoretically, the delta 47 value should vary inversely with the temperature, with the square of the temperature. So delta 47 expressed in parts per mil, so this is actually 0.6 parts per mil, 0.06%. It's a small fraction. Plotted across the top is temperature in kelvins, and across the bottom is the inverse of temperature squared with a factor to make the units or make the dimensions or the values here sensible. And you can see a bunch of different samples show a straight line. A straight line is fitting the theoretical curve. So this seems to work very well, getting temperatures from delta 47. So plotting that calibration curve again, but now writing it in terms of degrees C, one has a bunch of data that have defined the calibration curve. One then measurements based on lots of data for that. One has a sample from the field, measures the value of delta 47 here, plots on that line, and extracts a temperature from this. She has done all this work. She'll tell you it's a lot of work, but it's worth it. And it actually gains you a little bit more. If we go back to the oxygen 18 in the precipitation depends upon surface elevation, as we mentioned. But that's not what we measure. Of course, temperature depends on elevation, but that's not what we measure. We measure oxygen 18 in carbonate sediment, and the oxygen 18 in carbonate sediment depends on temperature as well as the rainwater that fell. So the delta O18 in the carbonate isn't necessarily, it's definitely not equal to what's in the water. It's been fractionated in such a way to be different, and that difference depends on temperature. But if we can measure temperature with clumped isotopes, we can know that quantity. And if we can know that quantity, we get this, we measure that, but then we also get the oxygen 18 in the water, the rainwater that's fallen, that's ultimately been combined into the carbonate sediment. So we get a better estimate of the delta O18. So this is a benefit that comes with this. And if we go back to the Bolivian Altiplano, where Carmen Garzioni did her work, and her work was based on oxygen isotopes, these are estimates of her data showing paleo elevation changes going back over time. The green are from paleobotany from Kate Gregory, and these reddish boxes are showing you the inferred change in elevation measured with temperatures, so one has to be a little bit careful. The temperatures, but correcting those temperatures. And the key fact is there's an abrupt decrease in temperature over the same period, 6 to 10 million years ago, as there is this change in oxygen 18. So the data are consistent with one another, and both are showing a rapid increase in the elevation of the Bolivian Altiplano between 10 and 6 million years. So clumped isotopes, these are direct estimates of temperatures, and they're temperature-sensitive clumping of these two together. That's the key. The weakness is the method relies on our ability to translate a temperature change or temperature difference into an elevation change. And this is still a problem because surface temperature depends on elevation from as little as 3 degrees C in moist tropics to 10 degrees C per kilometer, 3 degrees C per kilometer, to 10 degrees C per kilometer in cold polar regions. And so one has to be careful. But this introduces an error, but it doesn't make it's still, the method is very good. So another way of going at this is what are called branched dialkyl glycerol dialkyl glycerol tetraethers, hard to say, GDGT. So they're GDGTs, and the BR will be from branches. These grow in soils. They accumulate in soils because bacteria form them in the soils. And so I put a picture where you can see some vegetation with soil. And since this is my last lecture, I thought I should put something in about some of the beauties of Colombia. So I have no training in this, so I'm relying very heavily on slides from Francine Peters, a Dutch biogeochemist, from whom I got these slides. She's an expert. So the way this works is, in the soil, there are bacteria, and the bacteria they're small organisms, and they have cell walls, and the cell walls are made of lipids, these water insensitive molecules that have a head and a tail, and they consist of many, many carbon atoms in a loop, but with a head and a tail at the two ends. So as an example, here is one of these things blown up. There's a carbon atom at every one of these intersections. But then they're different from one another in small ways. They all have branches going off, a few branches coming off. So this has 4 branches. This has a 5th branch, and this has a 6th branch up here. So 1, 2, 3 refer to 1 branch, 2 branches, and 4 branches, 5 branches, 6 branches. They also can have these pentyl groups in here. No pentyl groups, 1, or 2 coming in here. And it turns out that, oh yes, there they are, pentyls, and then the next one blows up the pentyl groups down in here. It turns out the temperature decreases with more branches. Fewer branches means a warmer environment. And I'm not going to go here, but the higher soil pH, the more pentyls. This I will omit in further discussion. But if we focus in on this, these are gas chromatograph, I think it's gas, not liquid chromatograph measurements, where this big red peak is this 1A, the one with 4 branches down here. And notice this is low latitudes. This is a very warm environment. As you go to higher latitudes, France or Scotland, you still have the 1A with 4 branches, but the 2A becomes pretty important, the one with 5 branches, and the 3A is becoming important with the 6th branch, that branch up in here. And when you go to high latitudes, in fact, the one with 5 branches, this one is more significant. It's a larger fraction than the one with 4 branches. So one can use this to infer temperature, and from temperature then try to get estimates of paleoelevation. This has got limitations. Big errors so far with global calibration, 4 degrees C. That would be a 1 degree, at least, 1 kilometer error in elevation, at least, if that were the only source of error. We can get smaller errors with local calibrations in the tropics. And this, I point out, this is work by Lina Perez Angel, a Colombian who worked with Julio Sepulveda, a Chilean, in fact, here in the University of Colorado. But again, we have to translate temperature differences into elevation differences. So there is a limitation in applying this. But this has a bright future, some of us think. I certainly do. Okay, let's switch and go to a different direction. Vesicles in lavas as a paleoaltimeter. When lavas erupt, there are gases in the lavas, and they leave pockets or vesicles. Vesicle is just a little pocket that remains as a hole in the lava. The sizes of the vesicles decrease with depth in the lava because they reflect a balance between the gas pressure and the weight of the overlying lava. The deeper, the thicker the lava, the smaller the gases at the bottom, because the weight of the lava compresses those gas bubbles, makes them smaller. This is, I think, simple. But it turns out even with lower air pressures at high altitudes, the size of the vesicles offer the potential to get at air pressure. The variation in air pressure with altitude is small compared to the variation of pressure within a lava, or they're comparable anyway. So imagine a basalt flows out. It's quenched at the top because it's in contact with the atmosphere. It's quenched at the bottom because it's in contact with cold surface. You may still be plenty of liquid or viscous flowing lava in the middle. But at the top, the pressure is atmospheric pressure. The bottom, the pressure is atmospheric pressure plus the weight per unit area of the rock above, the density of the lava, rho, gravity, times the thickness, the weight up in here. And pressure, as I said, is inversely proportional to volume. Increase the pressure, increase the weight per unit area. and the volume will go down. This is, of course, goes back to the perfect gas law, or the ideal gas law, where the pressure times volume is the number of molecules times the gas constant times the temperature. We don't have to worry about that here. But the logic is that the pressure is inversely proportional to the volume, and V here would be the average volume of individual bubbles. One would count hundreds of bubbles and then take the average volume. And if that applies, we can take these two relationships, the pressure at the top, atmospheric pressure, times the volume, the average volume of the vesicles at the top, should be equal to the pressure at the top plus the weight per unit area of the lava times the volume at the bottom, and one can solve this for the atmospheric pressure. This is an application to modern flows in Hawaii, and it looks pretty good. Low elevation, this is the actual elevation. This is the inferred elevation from the vesicles in the lavas, and you get a very good fit. You're not going to worry about that kind of scatter. Does this work? Well, I have doubts, and maybe you shouldn't have doubts, but I do. Its virtues are it measures pressure directly. That's really good. And its quoted uncertainty is 400 meters, at least applied to modern lavas in Hawaii. That's also very good. We'll never be better than 400 meters in paleoaltimetry. Its weakness is it assumes the measured thickness is correct and not affected by inflation or deflation of the flow. So you can imagine if the flow, if lava drained from here out to the side, the surface would come down, then geologists would estimate a thickness, but it would be an underestimate of the thickness when the bubbles formed. Or the lava can be squeezed out and can inflate over here, and the measured thickness would be greater than the measured thickness at the time the bubbles were actually frozen into the lava. This, I think, is an important risk. And so it requires an understanding or a belief in the relationship of bubble sizes to the top and bottom boundaries. And here, viscosity of the lava is the crucial part, I think. If you imagine water flowing down a very gentle surface, the thickness of the water is very, very small compared to honey or molasses, some viscous substance flowing down a surface. The more viscous surface, the more viscous fluid flowing down will be thicker than the less viscous one. And so this method may work well when the lava has a low viscosity, but if it has a high viscosity, it won't. And hence the application will depend upon the viscosity of the lava. Okay, another method, cosmogenic nuclides. Cosmogenic rays striking nitrogen produce our carbon-14, which we use so much. They also produce beryllium-10 from oxygen, aluminum-26 from silicon, and chlorine-36 from calcium, as well as helium-3 from a whole bunch of elements in rock. It's in the rock that's important. So you have a cosmic ray coming in. It hits some target, a nitrogen, oxygen, or argon molecule, and it breaks it up. Neutrons come apart, protons, as well as mesons and muons, they come off. And they come down and they hit more nuclei, and they break them up and scatter. So there's an attenuation of the intensity of the cosmic radiation as you go down because of the scattering process that occurs along the way. And remember that beryllium-10 from oxygen and aluminum-26 from silicon, quartz is silicon dioxide. So quartz is an ideal sample. You can measure two of these cosmogenically produced nuclides in it. Okay, you have to remember these are radioactive. So beryllium-10, aluminum-26, chlorine-36, but not helium-3, have half-lives that are short. 1.4 with 0.7, 0.3 million years. So one can't expect them to last very long. As cosmic rays penetrate the atmosphere and then the rock, their intensity, hence their ability to split other nuclei, attenuates as they collide. That was this picture. But that means the production rate attenuates exponentially with depth through the atmosphere as well as into the rock. The production rate is higher with increasing pressure because it doesn't see so many atoms. once you go through more and more, or so many nuclei, once you go through more and more, you attenuate the energy of the cosmic radiation itself. And the typical E-folding depth, the factor of E equal 2.7, for a production rate are 1.5 kilometers in the atmosphere and 0.7 meters, 70 centimeters in crustal rock. The reason they're so different is these vary inversely with the density of the material. So the air is much less dense than the rock, of course. These two numbers are crucial. To give you an example, if you have a production rate P0 at the Earth's surface, production rate P equals 0, with this exponential attenuation, it means if you go up 1.5 kilometers, because that's the E-folding height, the production rate will be 2.7 times greater. And if you go up to 3 kilometers, the production rate is 7 times greater. And this is saying that, imagine if a surface rose quickly, it will have a lower concentration of cosmogenic nuclides than if it had been high at a long time. If it's high for a long time, it's accumulated at a high production rate, whereas the surface that rose quickly will have accumulated at a low production rate for much of that history. The formula that tells you the concentration of cosmogenic nuclides, beryllium-10, aluminum-26, whatever nuclide you have, as a function of depth into the rock, Z is depth into the rock, and T is time, consists of a part, if you bring the rock to the surface of the Earth, it starts with 0. It starts with a certain amount. This is at time 0, you bring rock that has some cosmogenic nuclides in it. It will decay radioactively, e to the minus lambda t. And if you're producing, of course, eventually the production will begin to the radioactive decay will cancel the production. So at time t equals 0, you have this initial value and you've produced nothing. And as time goes on, that decays, but the production increases. And then you have this exponential decay into the rock. That's what's shown with these symbols. And the E-folding depth of the rock, remember, is 0.7 of a meter. So first, the production rate, this number here, depends on altitude. And consequently, the concentration depends not only on the altitude, but the history of altitude change. So the longer you're high, the greater the amount of cosmogenic nuclides you'll find, because you've been producing it with a higher rate for whatever period of time has been there. But second, for large T, this simplifies, and this simplification is a sensible one. So if we let T be large, that quantity goes to 0, and that quantity goes to 0. And this equation reduces simply to the concentration depends on the production rate at altitude divided by the decay time constant, but then also decays with depth into the Earth, where this is 70 centimeters down here. So the concentrations of nuclei should be higher than lower altitudes, obviously, and especially if it's been high for a long time. And if the Earth's surface rose recently in geologic time, the concentration should be lower because it's been accumulating at a lower region. So let's take a good example, an extreme example, not a good example, an extreme example. Suppose we have 3 kilometers of elevation difference. That gives you 7.4 times more cosmogenic nuclides. Remember, the production rate at 3 kilometers is 7.4 times that at sea level. So if you raise the surface 3 kilometers in 1 million years, this is very fast, but if you did that, you would suddenly change the production rate by 7.4 times. That's a big number. But suppose you erode 1.4 meters. So while you're raising this surface 3 kilometers, you erode 1.4 meters in 1 million years. That's very slow erosion. That's 1 micron per year. This is almost an unmeasurable erosion rate. It's so low. But this factor in here, where rock that's now at the surface once lay 1.4 meters deep, and hence has a concentration reduced by e to the minus 2. That's this. It's reduced by 1.74 times. So in other words, the erosion of a tiny amount can nullify a huge elevation change in a short time. So even extremely slow erosion makes cosmogenic nuclides useless for paleoaltimetry. But there is one exception, useless. I describe this because people will develop this, but I think it's going to remain useless for a long time. Studies by Brown and Brook taking the approach did show that in the transantarctic mountains, where erosion is indeed extremely slow, this is very, very cold regions, there's no rainfall and there's no snow. So erosion, there's hardly an agent that can erode. And they showed that the transantarctic mountains that get up to 4,000 meters high did not rise substantially in the past 5 million years. They showed this because others had argued that the transantarctic mountains were really quite young. So they're not quite completely useless, but almost. Okay, the last of these tools, stomatal density of leaves, they depend on the partial pressure of CO2. So if you have a leaf, if you blow up the leaf, there are what are called stomata, these little features in here. And this is a photograph of a ginkgo biloba. This scale bar is 1/10 of a millimeter. So these are small, but that's a stomata. That's a stomatum, I think. That's another. These are stomata in here. They're only a part of the leaf. Most of the leaf is not stomata, as you can see. And stomata are essential because it's through these are holes in the leaf. It's through these that carbon dioxide enters the leaf. The leaf, in order to build the plant, has to take that carbon dioxide and take the carbon away and convert it into hydrocarbons to make the leaf. So the stomata are the places where the CO2 comes into the leaf, but unfortunately, they also are a place, well, fortunately, they lose their oxygen from here. This is why we can live. We get our oxygen. Ultimately, we get all of our oxygen coming through back out these stomata from these plants, but they also lose water. And hence, if they lose too much water, they dry out and the plant dies. So the plant has to evolve so as to have an opening that will allow enough CO2 in, but not enough water, H2O, out. And part of the way it does that is it closes these at night. So that you can't photosynthesize at night, so the stomata close at night, no water is lost. They open these in the daytime. So leaves take in CO2 and release O2 and H2O through stomata. With a higher concentration of CO2 in the atmosphere, fewer stomata are needed. The stomata let CO2 in. If you've got lots of CO2 in the atmosphere, well, you don't need many stomata. You can have fewer and still have the same amount of carbon dioxide coming in. And we can measure the amount of stomata in two ways. A stomatal density, the number per square millimeter, just count them up, or a stomatal index, and that's the ratio of the number of stomata to the total number of epidermal cells plus stomata. And this is a percentage. This is a fraction less than 1. If you plot some of these, and sunny sides and shady sides tend to be different, but here is stomatal density, the number per square millimeter, as a function of the CO2 partial pressure. A low pressure on this side, you have more stomatal density, more stomata per unit area, more stomata per millimeter squared. When the CO2 partial pressure is higher, you have fewer. This is true both in the sunny and the shady sides in here. Stomatal index, the same thing. This is the percentage. The percentage of stomata is higher when you have low CO2 because that actually surprises me. Oh, right, because you need more stomata. Right, you need more stomata when the partial pressure is low. When the partial pressure is high, you don't need so many stomata. And again, the stomata are a smaller fraction of the leaf. You could argue these data scatter quite a bit. Let's convert this into elevation. Here's plotted elevation and stomatal density, only stomatal density, number of stomata per unit area, millimeter squared. And you can see that as you go higher, partial pressure of CO2 decreases, the stomatal density decreases. Stomatal density increases because PCO2 is lower. Not so clear with the sunny side. And then what they've done in this is they've essentially changed the scale. So this point is moved over to the edge 1,000 meters and it looks better. You get more of a straight line going through here and more of a straight line. But the point is that the PCO2 decreases with elevation, and hence, in order for the plant to build itself, it needs to have more stomata or larger stomata, a larger area of stomata or more of them per unit area. This is from an oak tree of some particular kind. Now, this method is in some doubt. I show old data, stomatal index versus concentration of CO2 in parts per million. Old data, newer data are casting some doubt on this. I'm not in a position to evaluate this, but this is a concern. But if we summarize the strengths and weaknesses, its strength is it measures pressure, essentially directly, almost directly, because the PCO2 also decreases with an E-folding height of 8 kilometers. The quoted uncertainty is tiny, 300 meters. This is surprising. What I haven't said yet, but is essential, is this requires a calibrated taxon. In other words, you can't use an oak leaf to make your measurements in the lab and then go and find a fossil leaf that's a maple or some other taxon and use the same formula. You have to calibrate the fossil taxon. So the fossil leaf that you have to have a modern equivalent. If you don't have a modern equivalent, you can't do it. Therefore, it requires a taxon that's alive today, because if you're going to calibrate, you have to have that. And so that it can be calibrated and is found in the record. Plus, it requires knowledge of past values of PCO2, because obviously if sea level PCO2 was higher, PCO2 at high altitudes will be higher also. I think these concerns make it still a long way. It needs to be tested further. So if I summarize, and you might sense that I'm biased, I see clumped isotopes as the future, despite the difficulty of converting temperature to elevation. Branch GDT is also the future, and maybe ultimately better as the methods develop. I'm hopeful that this, in fact, will be so. Oxygen isotopes, they're imperfect, but they're not bad. They're pretty good. Leaf physiognomy, plus or minus really 1,000 meters, and leaves are not everywhere. This is good where you can do it, but it'll never be better than 1,000 meters. These others, I'm worried. I think the stomatal density is still inadequately tested. I would say the same of basalt vesicles. Still needs another test. It may work if we can know the viscosity of the lava that from which these are measured. And finally, cosmogenic nuclides. These are vital for many questions, but rarely, if ever, for paleoaltimetry. And I say rarely, but there is that one example that I gave you. And I have finished with, well, I'm sorry to say, only 3 minutes. I hope I didn't go too long. Back to you, Hector.
Thank you, Peter. Are you hearing me?
Yes, yes.
Thank you very much for that very interesting talk. Definitely, there are too many things to that this idea now exactly what is possible to do. I think that most of the audience will be thinking about these new techniques related to paleoaltimetry and how to be used, to be implemented in our country. This is a very good challenge. Let me see if there are questions, Peter. No, there are no questions, Peter.
Okay.
I think that we are everyone admiring what is possible to do. Thank you very much for all this tremendous stuff, very interesting stuff, Peter.
Well, I hope some of you have benefited in some way. For me, preparing all of this has not been a waste of time, because it helps me understand better what I think I know and then ultimately find I don't know.
Yeah, there are at least the first the results with this girl from Colombia working with you there. So this is a good beginning.
Yes, I agree. Yes, no, she's doing well.
So it is necessary to follow that path for many students that maybe they are attending this very impressive talks about the new trends and the new opportunities for research. Anyway, thank you again very much.
Okay, I will close down my screen here, and now I can't see you, as we know. So have we finished, Hector?
Yes, sir.
And if I stop sharing, well, I see my face. I don't see Jose David, but anyway. So what shall we do? You asked if I could have a look at. So I assume this is the last lecture. You asked if I could discuss GPS. I presume that would be just a small group of you and others. Do you still want to do that?
Yes, yeah, but it doesn't mean that it has to be very soon. I would like to prepare some maps and probably to send you in an advance with some questions, and after that we can schedule some meeting. Depends on your time. We can learn how to interpret some vectors, maybe some ideas what is necessary to emphasize in our research, thinking in the future for 2022 to see what is possible to do, maybe to do something together, that we have some questions that are still in the back. So maybe this is a good opportunity for us to learn from you, Peter.
No, I'm happy to look at whatever you have, and there's no hurry, as you said. When you have stuff, you can send it to me. That's fine.
So we are trying to finish processing the data at least until October. So the idea is to have the more extended set of data from the different stations. And also one thing that is good to start looking at is at the vertical component. That I think that some of the stations already have enough data, 5, 7, some 8 years. So maybe we can start looking for some vertical strain signal or something like that. I don't know. We have to figure out how to work with that.
Yep. I agree. That it is a challenge, though, as you know.
Yes, that is a big challenge because we are looking all the time with the horizontal velocities and so far, but I think that it's better to introduce in the scientific research of the GPS in Colombia the vertical stuff in different areas, especially in the Caribbean coast. We started looking in some parts the subsidence, and the other parts are looking for uplift. So that is very interesting to start looking at the specific detail, or maybe what is the related phenomena for some explanation about that.
Yep, I agree.
And there is another thing that I think that I would like to recommend you to talk with Dave, because it's necessary to finish that paper.
Yeah.
That paper is very important.
Well, I'm not part of that paper, so I'm not in a position to push him, I don't think. But yeah, I could send him a note.
No, I agree. I think that I know that you are not part of that paper, but he listened you very well.
Yeah, we were hoping Roger would be back, but Roger's still in California. I was hoping we could get together with him. But okay, I'll send Dave a note, and I'll just tell him that we talked, and you're eager to see him finish the paper.
Yeah, because he was working a lot on that. Basically, his PhD thesis is one of the chapter, so he deserves to publish that.
Yes, I agree.
I don't know. I don't see the reason why not to do that. I understand that because he got a new position that he's very busy. By the way, I think that I have talked to him. I think 2 or 3 times this year. He disappeared of the panorama.
Yeah. Yeah. No, with COVID, we don't see much of each other, but yep, I'll send him a note. I'll do that. I'll do that today.
Okay, Peter. The stuff that you showed today is very impressive. Oof, too
So
many things to do.
can I just ask you one last question? Maybe this question will be embarrassing for you to answer, but how many people are listening to these lectures?
Well, I don't have the opportunity to see, but you say in every talk, directly talk, I think that sometimes we have 50, 60 people, 35, depends on that, depending on the talk. But the most important thing is the people start looking on YouTube and love the opportunities and repeat and repeat and repeat the talks, and depends on where they like. uh, and sometimes I did that we can say some statistics about that, but that I recall that he told me sometimes more than
Yes.
300, 350 people watching the talks.
Yes, Pete. In the all the most streamings for your speakers, there are around the 100, 200, or 300 views in all the the records. So
Mhm.
it's a good statistics, and maybe we can do the a chart
No,
with
no, I
all
no, don't.
statistics if you
No, no,
want.
don't go to any trouble. I just was curious. That's all. You don't have to do any work. It's okay.
Oh, okay, Pete. For
I,
all
I,
the
I can tell you that your talks are being watched in Japan. I know
Really,
that.
really.
Yes,
Oh
yes.
my God. Wow. Well, not live, obviously.
for all the communication group of the Geological Colombian Survey, it's a pleasure to work with you, Peter.
Oh,
We hope to work very soon with you again.
well, thank you. And enjoy Bucaramanga. It's not so high as Bogota, and it doesn't rain so much. And I was there 15 years ago, and that's a nice place to spend a bit of time.
Hi. Okay, Pete.
Okay.
Bucaramanga is a very nice site. Yeah,
Yes.
that is one of the cities that I will have to retire from Bogota, from the Geological Survey. One of the places I would like to live is in Bucaramanga City.
Yeah. Yeah. Yep. Right above the nest, the puzzling nest.
Yes, 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 it is. Peter, I don't know what to say really. I want to really to appreciate your effort and your help for the Colombian people, and it's not from Colombia. I know that these people is watching these your talks in different countries, Panama, Venezuela, even in the United States. Some of the Colombian people that is studying there, they are watching this. So really, I am in debt with you because you open your heart in order to help the Colombian community. I want to express you again, again, again. Thank you very much for for understanding what our needs are, why we need to start looking for the new trends, new technologies, new techniques in order to understand what the geodynamics in our territory. So there are too many things to do. Wow. But at least this is a good start, maybe for some people to introduce in this new stuff. Thank you, Peter.
Well, you're welcome. As I said, it's not been a waste of my time. So I'm glad it hasn't been a waste of my time. I appreciate those thoughts. Okay, it's the end of your workday. You guys, Jose David has already taken his mask off. He must be the only one left in the office.